Hello everyone, my name is Dr. Vern Harner. I'm an assistant professor in social work, and I am offering y'all this mini refresher in basic statistics for social workers. So if you are an undergraduate or graduate student in social work, maybe even you're starting your PhD, this is a very quick refresher. So there is the huge caveat that this is going to be simplified. I hope that it will only be about 15-20 minutes long at the longest, so we will see. But I wanted to offer this because it's something that I know can be hard to get a grasp of, or maybe you took a statistics class a year ago, 5 years ago, 10 years ago, and now you're struggling to remember some of these things. So here we go. Let's get right into it. First of all, what do we even mean when we say statistics, right? What is that word? We are almost always talking about quantitative research when we use the word statistics as social workers. Statistics, then, is a branch of mathematics that involves the collection, analysis, interpretation, presentation, and orientation of data. It provides a set of methods and techniques for making inferences from data and for describing the uncertainty that arises in those inferences. Statistics is widely used in various fields, including the hard sciences, business, social sciences, government, but also in everyday decision making. Statistics play a crucial role in scientific research, decision making processes, quality control, policy development, and more. Statistics help researchers draw meaningful conclusions from data, quantify uncertainty, and make informed decisions based on the evidence. The application of statistical methods is diverse, ranging from clinical trials in medicine to market research in business, and of course from social science studies to environmental monitoring. So you can see this is quite a broad swath, and there are a lot of resources out there on the internet. I've always struggled to find resources specifically meant for social workers, which is why I decided to create this mini refresher. In statistical research, a variable is defined as an attribute of an object or of study. Variables can be controlled or changed, and they can be measured. As researchers, it's really important that we are thoughtful when we're choosing which variables to measure. So a lot of time and energy goes into that. And so these might be words that you remember hearing at some point. Independent and dependent variables, or the X and the Y. The Y variable, the dependent variable, it depends on the X. The dependent variable is the outcome variable that the researcher is interested in measuring. So on this graph, right, the x-axis is horizontal on the bottom, and the y-axis is vertical, and then we have that little squiggly line that is representing the relationship between those two variables and all the values in them. So let's use a quick example. All the examples in this presentation are fake, they're made up, they're not real things, okay? So there's another caveat for you. So let's look at the impact of income on health. So as a researcher, I'm interested in learning more about the health of people, right? That is my outcome variable. And here we can see that as someone's income increases, health is also generally increasing as well. So then as a researcher, I would, dig deeper into this and try to figure out why and what exactly is happening and all of that. But here we are looking at the impact of income on health, where health is the dependent or outcome variable. And of course, there's lots of different things that variables can be, right? Not all variables are the same. And so as researchers, there's quite a lot of controversy around these categories as well. but we have 3 or 4 main kinds of variables or levels of measurement. So variables can be discrete, that is, they can be whole counts, integers, whole numbers. For example, the number of students in a class. I'm not going to have half of a student, hopefully. Or variables can also be continuous, such as distances or volume or ages. So those numbers can be broken down into smaller numbers. But just having those 2 categories doesn't really give us enough categories to categorize all of the variables that we have in our data sets. So we have these 4 kinds of variables: nominal, ordinal, interval, and ratio. And you can see here, this is a general overview of the qualities of these different kinds of variables. So for nominal variables, I always think of these as named variables. They're names of things. So something like colors, right? Red, blue, orange, yellow. They are mutually exclusive categories. They cannot be rank ordered, meaning red is not better than yellow, so I couldn't put it in any specific order. They are not equally distanced from one another. That doesn't really quite make sense. And there's no true 0 point, right? So that is nominal data. Ordinal variables, then, these can be put into an order. So if you've ever heard of a Likert scale, those are the questions where maybe your doctor has asked you on a scale of 1 to 5, what is your pain today? Those are also exhaustive, they're mutually exclusive, 1 and 2 are different numbers, and they can be put into a specific order that makes sense, right? 1, 2, 3, 4, 5, that's the order that makes sense for us. Then we have interval variables. So for these, it's all the stuff that applies to ordinal, but they're also equally distanced from one another. So a good example of interval level data is the temperature when it's in Fahrenheit. So it is able to be negative. There's no true 0 point. Something could maybe be negative 500 degrees Fahrenheit. But the degrees in Fahrenheit are equally distanced from one another, right? The difference from 0 to 1 degree is the same as the distance from 1 to 2 degrees, and so on and so forth. And it can be put in a specific order that makes sense. It's exhaustive, it's mutually exclusive, so on and so forth. Then ratio level data. This is the same as interval level data, except there is a true 0 point. So here, something like someone's height, right? There is a true 0, or the length of time, where 0 actually means 0. I'm not going to get into a big philosophical discussion here about, if there is negative time. For the sake of this discussion, there's no such thing as negative time. So the length of time would have a true 0 and would be ratio level data. Next, say that we have a data set with, say that this was a Likert scale, right? We have some data in our data set, and we want to learn more about our data set and the data in it. What is the tendency of the data set? If I were to put all these numbers into a bag, close my eyes, stick my hand in, and pull something out, what would it likely be, right? What is the tendency of the data set? What is the mid value? What is the most common value? What is the average? This is actually a pretty complicated question statistically, which is why we have multiple measures of central tendency. The main measures of central tendency that we have are mean, median, and mode. So the mean, the average, that's the sum divided by the total number of values. That is the measure of central tendency that is most impacted by outliers. So in this very small made-up data set, the average is 4.1. But if we take the median, which accounts for those extreme outliers, the 2 9s on the end there, the median is 4.0. Now the median is the middle number in an ordered data set. Next, the mode is the most frequent value in the data set, and sometimes this is really useful information. So in this data set, it is the number 1, which we have showing up 3 times, whereas other numbers only show up once or twice. But I want to know even more about this data set. What is the variability of the data set? What's the variance, right? How are these numbers different? Are they all scattered around? Are they clumped together? Are they on one end of the scale? Tell me more. So for variability, we also have different ways of answering that question, right? The question is, how spread out or scattered are the values in the data set? More than one way to look at that. So we might look at the range or the standard deviation. In this data set, the range is 8. That is the difference between 1 and 9. So 9 minus 1 is 8. If we had a 0 in this data set, then the range would be 9. Now, standard deviation is a little bit more complicated. The standard deviation is the average distance of the values from the mean. So for this data set, that is 2.9. And if I were going to calculate this by hand, which I have done before, we're all capable of doing it, maybe with a calculator, but it actually involves taking the squares and then adding it. It's a whole thing, right? It's a whole thing. But luckily we have computers, software that can do that for us. So basically the standard deviation is the average distance of all the values from that mean, which is 4.1, right? And so in this data set, the standard deviation is 2.9. So why do we care about that, right? What does that mean? Why do I care about standard deviation? Standard deviation actually tells us a lot about our data set, especially if we're working with really big sample sizes or certain kinds of data, or if we're working with data that are normally distributed. So remember that bell curve, right, where it goes up and then the biggest part is in the middle and then it peters back down again. In a normal distribution, so in a bell curve, just over 2/3, 68% of the values in that variable lie within 1 standard deviation from the mean, right? So again, our mean, our average was 4.1. So 4.1 plus 2.9 is 7, and 4.1 minus 2.9, that 2.9 is the standard deviation again, is 1.2. So in a normally distributed data set, just over 2/3 of the values lie within 1 standard deviation from the mean. And we can take it a step further. In a normal distribution, 95% of the values lie within 2 standard deviations from the mean. And you guessed it, we can take it even one step further. In a normal distribution, 99% of the values lie within 3 standard deviations of the mean. I think that this is really 99.7 or 99.97, something like that, but it's a lot, right? So this is really exciting and important to know if you're working with big data sets, if you're working with certain kinds of data, things like that. But the standard deviation you'll see throughout the rest of statistics used in different ways. Next, we're going to quickly discuss correlation versus causation and then talk a little bit more about correlation. So you might have heard, right, correlation is not equal to causation. Even that is a statement that there's been a lot of discussion about. But basically it means that just because there's a relationship between 2 variables, it doesn't mean that one of those variables is causing the other variable to be true, right? And we'll have an example later. So the correlation, again, tells us the strength and direction of the relationship between 2 variables. So in this scatter plot, you can see these data points. They're all scattered around. There's no rhyme or reason. There is no relationship between these two variables. They are not correlated with one another. But if they look like this, we would say that there is a strong positive correlation between these variables. What that means is that as one variable increases or goes up, so does the value of the other variable. One goes up, the other goes up. One goes down, the other goes down. There can also be a negative correlation between variables. So that means that as the value of one variable increases, the values of the other variable decrease, right? One goes up, the other goes down, the opposite way. And when we find a correlation using a statistical test, we come back with a correlation coefficient, so an actual number that tells us the strength and direction of that relationship. So those coefficients are between -1 and +1. So if it is -1, or I'm sorry, if it's +1, then they are perfectly correlated, meaning if one thing is true, then the other thing is also always true. So if they're anywhere in between, then that tells us about the strength of the relationship there. So closer to 0 means closer to having no relationship between those variables. And so what you'll notice about a correlation table of results is that it's a mirror image along that diagonal line, right? And that's because if you look at the title of all the rows and the columns, right? It goes introvert, extrovert, dog, cat, and then going down, introvert, extrovert, dog, cat. So introvert and introvert, when those intersect, that is going to be perfectly correlated because it's the same variable. So these results are showing that in this made-up data set, again, not real data set, I don't know if this is true or not, don't go quoting this off over the dinner table, but what this is showing is that the variables of being a cat owner and being an introvert are positively correlated with one another, whereas being an introvert and a dog owner is negatively correlated with one another. And because those are pretty big coefficients for this kind of data, this fake data, we can say, wow, it's a moderate or a strong correlation. But then we see that being an extrovert and being a dog owner are also positively correlated, but that number, 0.29, it's not a super huge number. It's not super close to 1. So I'm curious, is that actually true? Can I generalize it to the whole population? Is it due to chance? Is it just who decided to do my survey that day? Was there a sampling error or a bias, right? So we're going to talk about that as well. Now here it's important to note, remember, correlation does not equal causation. So just because you're an extrovert, it does not immediately cause you to go out and buy a dog. Or just because you're an introvert, right, does not immediately cause you to go out and get a cat, right? That's not causation. We're just saying, are these two things related to one another? Let's find out. So when we look at the variables of extrovert and dog, again, is that up to chance? What do you think? How do we find out? The answer is more statistics. What we are asking is if those results reach statistical significance. Are extroverts actually more likely to own dogs? One of the main ways that we discuss statistical significance in social work research classes is probability values, which we call p-values. So this value is a calculation of the likelihood that our results were up to chance or due to certain kinds of statistical bias or error. The result, the p-value, is actually a proportion or a percent. So if the p-value is 0.05, that means that there is a 5% chance that our results are due to chance, sampling errors, some kind of statistical bias, etc. That means that a smaller p-value tells us that it is unlikely the results of our analysis are due to chance. So there's no universally accepted threshold for what is and is not a statistically significant p-value. So when you're reading different research articles, you might see 0.05, 0.01, 0.001, you might see something else. We often see researchers indicating p-values at the 0.05, 0.01, and 0.001 levels though. And you can find p-values either in the results table, or sometimes if it's a table like this one, they might be indicated by an asterisk or multiple asterisks. And the researcher should tell you what those different asterisks mean in the footnote of the table. So here we can see that it is unlikely that it's due to chance that extroverts are owning dogs here. But I would still, want to learn more about this because it is still just, maybe a moderately strong relationship here, depending on our sample size and all of that. So as a researcher, I would still be interested in learning more about the relationship between those two variables. So that was a super quick refresher course on statistics for social work students and social workers. Again, huge caveat that I oversimplified things. This was just a mini refresher or perhaps a basic introduction. And a lot of social workers might be wondering, why does this matter? If you're not a researcher or a statistician, why do you need to know all this? So as social workers, our practice is informed by practice wisdom, lived experience, but also by empirical data. All of those things help us decide what to do in order to best serve our clients and communities. By having a foundational knowledge of these statistical concepts, we as social workers can critically evaluate research studies, we can assess the effectiveness of interventions, and we can make evidence-informed decisions in our practice. Right? Maybe you've heard of evidence-based practices before. Well, you can actually go and read the studies that said whether or not those practices and programs actually work or not. Or maybe you're working on a program or you're leading a social work program. You can use statistics to help you evaluate the effectiveness of that program so you can always be improving it. As we work with our own culture, but also other cultures, we can always become more attuned to culturally competent and humble practices. So if we are able to read the actual studies that show, oh, these practices worked really good with this culture, or people from this community and this culture actually vibed more with these practices, being able to really understand the results of those studies is so important for social workers. Last, autonomy and empowerment. Being able to understand this on your own is so important. We've all heard the phrase, knowledge is power, right? So this gives you just a little bit more knowledge, a little bit more power as a social worker. I hope that this was a helpful mini refresher for you. Here are 3 of my favorite resources for statistics. The Scriber or Scriber.com page has a lot of information about statistics. There's this free textbook available by DiCarlo and 2 other co-authors that is available online. And then there's also this super helpful statistics guide if you are actually digging into statistics yourself. Maybe you're in a research class, or you're starting your PhD, or you're starting being a professor, anything like that. The information in that stats guide has been invaluable to me. So again, I hope that was helpful, and thank you so much for making it to the end.